Well, hello there and welcome to Chapter 8, Part 2. The first part of Chapter 8, we went and put polynomials together. We added, subtracted, and multiplied. In Part 4, we're going to spend this whole half of the chapter working on dividing polynomials, or what I'm going to call factoring. What is factoring, you say? Well, factoring is taking a polynomial and breaking it apart into smaller pieces. You could also look at factoring as the opposite of the distributive property, or as the opposite of what we did the last couple of sections. That, of course, means that all of your answers for factoring should include some sort of parentheses. However, before we get to factoring, we've got to go ahead and talk about some of those basics. Let's start with prime numbers. Hopefully you've heard about prime numbers before. A prime number is a whole number greater than 1 that has only two factors that are 1 and itself. Some examples of prime numbers is going to be 7, 17, 31. If you think about those numbers, one way I like to think about it is, can I divide anything, can I take that number and divide it by anything and get something even out? Something that's another whole number out. Of course, everything, well, not everything, but almost everything in math has some sort of opposite. The opposite for prime numbers is what we call composite numbers. It's a whole number greater than 1 that has more than 2 factors. So let's go ahead and highlight our differences here. Prime numbers have only 2 factors. Composite numbers have more than 2 factors. Some other examples for composite numbers could be something like 9, 16, or 18. So if I go back to what I was talking about earlier, I could look at 9 and say, well, 9 divided by 3 gives me 3. So I know it's a composite number. 16 divided by 2 gives me 8. I know it's a composite number. Let's have a little reminder here. A factor. When 2 or more numbers are multiplied, they are called the factor of the product. Basically, if you can think of 2 numbers, let's say 2 and 4. 2 and 4 gives you 8. So that means 2 and 4 are both factors of 8. So let's go ahead and look at some of these practice problems and see if we can find how many factors they have. Here's the way that I found the most orderly to do this. I start at 1 and say, okay, well, 1 times what gives me 22? Well, that's nice. 1 times 22 gives me 22. Then I go, okay, what's next? 3 definitely doesn't work. How about 2? 2 times 11 gives me 22. Now let's keep going down that line train of thought. Is there anything between 2 and 11 that when multiplied together gives you 22? That's whole numbers. I can't think of any. So if I was to go ahead and list all of these out in a nice line, I can go down this column and then up that one. So 1, 2, 11, 22. Basically what going down and then up is when I write it in that order, putting it in numerical order. Now, how many factors does 22 have? I'd say it has 4. And since it has 4 factors, I know 4 is greater than 2. So I can say 22 is composite. If we were to look at 31 and pretend that it's not on our list of examples for prime numbers, I could look at 31 and go through the same process. 1 times 31 And I'll find that there's nothing else between those two numbers that multiply to get me 31. So my list will be nice and short, 1, 31. It has two factors. Of those two definitions, one says only two factors, and that would be prime. So I would say, okay, well, 31 is prime. Now that we know about prime and composite numbers, we can talk about prime factorization. Prime factorization is when a number is expressed as the product of only prime numbers. Basically, I take that number, break it down into just the prime numbers that multiply to get me there. How will we do this, you say? Well, let's make a factor tree. If you don't know what a factor tree is, or if you've never been there before, that's okay. We'll do a few of them in the notes today. And if you have any questions still after that, feel free to ask. I'd love to help you. So let's go ahead and do an example. It says find the prime factorization of negative 132 x squared y cubed. Wow, that's a lot. Well, let's take it up and break it into smaller pieces. I see that I have a negative sign here. That negative sign tells me that my prime factorization is going to start with a negative 1. Then I can go ahead and look at my number, 132. I'm going to write that number off to the side and make a factor tree, 132. Now to start our factor tree, you can think of any two numbers, any two whole numbers that multiply to give you 132. I like to start small. I see it's an even number, so I'm going to start with 2. I know 132 is 2 times 66. I also know 2 happens to be a prime number, so I'm going to go ahead and circle it. Then I will look at 66 and say, okay, two numbers that multiply to get me 66. Easy. 6 times 11. Well, I know 11 is a prime number. I'll go ahead and circle him. But 6 is not. 6 I could write as 2 times 3. And then 2 and 3 are finally two prime numbers. Once you get to a point where every branch ends with a circle, you're going to take those numbers and write them in numerical order. However many there is how many you should write. So for example, I have 2 times 2 times 3 times 11. Hold up, we're not done yet. We still have those exponents here, or those variables with exponents here. We're going to take a flashback all the way back to chapter number 7, where we started with the very first section. I said, well, squared means write it twice, right? So that's what I'm going to do. I see an x squared, so I'll write 2 x's. I see a y cubed, so I'm going to go ahead and write 3 y's. I broke that apart into smaller pieces, looked at it, and found my prime factorization. Now let's look at number 3. If I start with A, I could find my prime factorization of 84. Let's go ahead and do that with a factor tree. If you can do it without a factor tree, kudos to you, but I'm still going to walk through a factor tree because sometimes there's a lot of numbers and I don't want to lose track of any. So I know 84 is 2 times 42. I know 42 is going to be 2 times 21. You can go back and circle both those 2's, they're prime. And I know that 21 is going to be a 3 times 7. 3 and 7 are both prime numbers as well. Circle those. Everything ends with a circle, so let's write them all down. I have 2 times 2 times 3 times 7. Now let's find the prime factorization of 30. Start my factor tree with my number 30. 30 is the same thing as 3 times 10. 3 is prime. 10 is the same thing as 2 times 5. 2's prime, and 5's prime. Now let's go ahead and write those in order again. I have 2 times 3 times 5. The last part says, what is the largest number that is a factor of 84 and 30? Well, here's how I'm going to look at that and do that. I will take anything that is in both of them and circle it. I have a 2 in both of them, and I have a 3 in both of them. Those are the only things they share in common. So I'm going to say, well, 2 times 3 is equal to a 6. If you could have told me it was 6 without doing the prime factorizations, then I'm going to look at you and say, you know your times tables? That's awesome. Go ahead and do it that way. If you can look at them and tell me it's 6 right away. But as we start to work with larger numbers, you might want to remember how to do it this way because you might not know the largest number off the top of your head. However, that 6 is a very, very important number. He is what we call our greatest common factor. What are the rules for the greatest common factor, you say? Well, the greatest common factor is the greatest number or our largest number and variables that is a factor of all the given numbers. In order to find this, we can do exactly what we just did in exercise 3. Write the prime factorization of each term and circle the common factors. Then go ahead and multiply them. So if we were to go ahead and do example number 4, you might look at 12 and 8 and tell me, well, their greatest common factor is 6. If you can do that, awesome. Go ahead and do that. I don't need to see the rest of the work. For those of us that can't, I can say 12 is 2 times 6 and 6 is 2 times 3. Circle all my prime numbers. And I know 12 is equal to 2 times 2 times 3. If I looked at 18, made another factor tree, say 18 is 2 times 9. 9 is 3 times 3. So I know 18 is going to be equal to 2 times 3 times 3. Go ahead and circle what they share in common. They both have a 2, they both have a 3. And let's multiply those two things together. 2 times 3 is equal to 6, which is, of course, my greatest common factor. Hopefully you can do this. If you find this difficult or have any questions, please ask, because factoring will get a lot harder if you cannot find your greatest common factor. So let's go into talking about the first form of factoring that we're going to do. The first form is going to kind of be like the anti-distributive property. Now let's make sure we remember what the distributive property says. It says I can take my 5x, multiply it by my 3, and my 5x, multiply it by my 5x. And of course that would give me a 15x plus 25x, don't forget your squared. That's basically what we were doing last section, right? It's doable, we remember doing this. Well, the part that's going to be different today is that we're going backwards. Our problems will look something like this, while what our answer should look like is something like this. Because when factoring, our answer should always have parentheses. Today for factoring polynomials, we'll work with binomials and trinomials for the most part. We're going to look at factoring polynomials and we'll say, today, find the greatest common factor of all of your terms. Once you have found that greatest common factor, go ahead and write the greatest common factor down and then open a set of parentheses next to it. The final step is going to be divide each term by the greatest common factor, and then write that inside the parentheses. So here's what I'm going to say. If you are one of the people that like prime factorization, that little bit of extra work you did at the beginning is going to pay off. Because instead of divide each term by the greatest common factor, we can go ahead and say multiply leftovers. And we'll take a look of exactly what that looks like in just a second. I do have one more point about factoring for you today. In today's factoring, and I do mean today's, this won't always be true, but if we're talking about pulling out a greatest common factor, the number of terms you started with should be the number of terms in the parentheses. So of course, let's go ahead and go through a couple of example problems. We already know what the answer for number 5 should be. It's that example from the distributive property up above. So let's go ahead and do number 6. If I do number 6 with a factor tree, I am going to have 4x. Well, 4 is 2 times 2. So I know that my prime factorization of 4x is going to be 2 times 2 times x. I could also look at my negative 32. Well, it's negative, so I know automatically I'm going to start with a negative 1. 32 is going to be 2 times 16. I know 16 is 2 times 8. 8 is 2 times 4. 4 is 2 times 2. 1, 2, 3, 4, 5. See how that could be a really easy, I accidentally forgot to write one down when I'm doing it all in my head? Let's make sure we write down our 5 2's. 1, 2, 3, 4, and 5. My next step for finding a greatest common factor, circle anything that they have in common. This one has a 2, this one also has a 2. I found a 2 here and a 2 here. Do they share anything else in common? No, they don't. So I'm going to say that my greatest common factor is a 2 times 2, which should give me a 4. All right, step 1 on our list is done. We found our greatest common factor. Step 2, write it down and open some parentheses next to it. Done. Here's what I was saying about writing out the prime factorization, making it easier in those leftovers. I've got 2 options. I can look at those leftovers and say, okay, well, 4x leaves me with an x. So I'm going to put an x in the parentheses. I could also look at it and say, okay, well, 4 times what gives me 4x? What am I missing? As for 32, I could look at 4 and say, okay, 4 times what gives me negative 32? Well, that's a negative, what is it, a negative 8? Or I could look up here at my leftovers and say, okay, I have a negative 1 times a negative 2, that's negative 2, times a positive 2 gives me a negative 4, and of course a negative 4 times another 2 gives me a negative 8. Now let's double check, make sure that I can close those parentheses and that I am done. I started with 2 terms. Inside my parenthesis, I have 2 terms. So I can go ahead and close it off and say that I am done. Let's do one more. Let's look at number 6. I am going to write out the prime factorizations without the factor trees for number 6 just to save us a little bit of time. If you would like to pause and write out those factor trees, then go ahead. I know that 12a squared is going to give me a 2 times 2 times 3 times a for that a squared. I also know that a 16a will give me a 2 times 2 times 2 times 2 times a. And finally, if I look at 4, I have 4 is 2 times 2. In order to find my greatest common factor, let's circle everything that is in common in all of them. And that would be 2 2's. So I know my greatest common factor is 2 times 2, which is, again, 4. All right, first step's done. I found my greatest common factor. Next step, write it down, open some parentheses. I'm going to use the leftover method since I already wrote out the prime factorization. If you would like to take 4 and look at it and say, okay, what do I need to multiply to get to 12a squared? Feel free. But since I already have it written out, I can say, okay, well, I was left with a 3 and 2 a's. 3 times 2 a's gives me a 3a squared. I can look at 16a and say, okay, well, I'm left with a 2 times a 2. That gives me a positive 4 times an a. Don't forget him. Now here's the thing. If I look at 4, I don't have anything left. But if I look at my answer, I only have 2 terms, and I started with 3. Well, that means I still need to add on another term over here. Could I take this 2 times 2 and multiply it by a 1? Of course I can. It's not going to change anything. So that means that I was left with a 1. I'm going to go ahead and leave number 8 as an example for you to do. I do have a question before we wrap up these notes though. Why is 2a times 6a plus 8 not in factor form, where 4a times 3a plus 4 is factored? In order to find an answer to that, I want you to look right here and think about greatest common factor. If I was thinking about 6 and 8, do they have a greatest common factor? That's right, they do. Their greatest common factor would be 2. Since I still have a greatest common factor that is not 1 inside of my parentheses, I know that I didn't pull out everything that I can. So this is technically a step to getting to the right answer, but it's not all the way there. I could say that I have 2a times my 2, and then what's left, divide those out. 6a divided by 2 is going to give me with 3a. 8 divided by 2 leaves me with 4. Of course, I could multiply those out, and I would get my 4a, 3a plus 4. So, if you are not a big fan of having to do extra work, make sure that you find that absolute greatest common factor before you pull it out. Otherwise, it's okay, you're just going to have to do more work. That is all I have for you for 8.5a today. So, lesson summary. A personal question for you. How will you find the greatest common factor? All of these examples, I wrote out the prime factorization. But if you can just think about the factors and think about them in your head and find it because you know your multiplication tables, you can do that too. So which of those 2 options would you use? And don't forget to write down why. Why do you think you're going to use that option? If you don't have the why written down, I will be asking you as I try to stamp your notes. Also, don't forget, it is not possible for me to stamp your notes without having that practice problem done. So go ahead and factor 18xy squared minus 24x squared y. I hope that you learned something new today, and I will see you soon.